So as I said, first of all, you have to know the polarity of the molecules. So I will have to show you the structure of the molecule first. PF3. Phosphorus is in group number 15 with 5 electron valency. So with fluorine atom, very high En. No? So fluorine take away electron from phosphorus in order to fulfill the octets of the fluorine atom itself. So at the end, your phosphorus is used 3 of the electrons making chemical bondings. And then your phosphorus contains 1 pair of electrons left. So with 4 groups of electrons, your structure adopted the kind of tetrahedral shape. But anyway, because one of the clouds is electron pair, then the shape of the molecules is switched from tetrahedrals to be pyramidal shape. And from this structure, as you can see, if you want to draw the dipole moment of the molecules or the arrows like that, fluorines pull electrons cloud towards itself. So phosphorus lost its electron to fluorine. But the vector summation, right, you have to sum up 3 vectors together. So at the end, the polarity is pointing downward, right, perpendicular towards the ground. So this is the polarity of the molecules. Then we have PF5. But PF5, all 5 electrons of valence electrons of phosphorus is taken away by fluorine atom. So at the end, with 5 electron clouds, the molecular structure of PF5 or phosphorus pentafluoride is trigonal bipyramidal shape. So with the trigonal bipyramidal shape, what you can see is that we have trigonal planar, right, and the axial of the axial atoms. So at the end, all the vectors are cancelled. So that means the dipole moment of the molecule is 0, right, approximately. So by these 2 pictures, as you can see, PF4 is a dipole molecules, but PF5 is nonpolar molecules. Now we come to SF4 and SF6. SF4, because sulfur contains 6 valence electrons, right? But 4 of them are now taken away by fluorine atoms, make 1 electron pair left in your central sulfur atom. So as you can see, that the structure is composed of 5 electron clouds in trigonal bipyramidal shape, but because of the lone pair over here, then the structure, the name is shifted from trigonal bipyramidal shape to be seesaw, right? So as you can see from this, the axial is somehow vector is cancelled, but for fluorine, right, higher En, the polarity is pointing to the right towards the fluorine side. So this is the polarity of the SF4, right? This is polar molecule. But if you look at SF6, SF6 is a kind of octahedral shape because all 6 fluorine takes all 6 fluorine atoms take 6 electrons from your central sulfur atom. So at the end you have this octahedral shape. And because of 90 degrees arrangement of every fluorine atom, then the dipole moment is equal to 0. So as you can see, the left-hand molecules is polar, but the right-hand molecules is non-polar for both pair. But anyway, what I want to show is the boiling point of all 4 molecules over here. PF3, I would say boiling point in degrees Celsius. Okay. So the PF3 is minus 102, PF5 is minus 85. SF4 is minus 38, and then SF6 is minus 64. So surprisingly, these two pairs are not go along with each other. So as you can see, that the boiling point of PF5 is higher than PF3. But the boiling point of SF4 is higher than SF6. Why? Because actually, the factors for boiling point is the intermolecular interactions. But the intermolecular interactions is not only dipole-dipole interactions. We also have London force that we've already mentioned about it earlier, right? So PF5 and SF6 is higher in their London force because the molecules is bigger than this pair, right? Than PF3 and SF4. But for the left-hand molecules here, you have higher dipole-dipole interactions. So the first pair, because we have two factors, dipole-dipole interactions and London force, and they just fight against each other. And we cannot really point out with which kind of intermolecular interaction is more important. And as you can see from the examples here, that for the upper case, right, PF5 has higher boiling point. That means the London force is more important than the dipole-dipole interaction here. But for the bottom one, SF4 is higher in the boiling point. That means the dipole-dipole interaction is more important than the London force. So as you can see, sometimes when we have more than one factors and they are not going well together, right? They fight against each other. So sometimes we cannot predict the result, right? We cannot just predict by just looking at the shape and the dipole moment to say that which one has higher boiling point, which one has higher melting point. Okay, it's very, very hard to say. And this is the example. So as you can see, only one particular intermolecular interaction is not enough to explain the behavior of the compound. Okay, you may have to use more than one intermolecular interactions. Okay, so that's all about the dipole-dipole interactions. We will move on to other intermolecular interactions in the next video.